Welcome. In this video, we're going to take a look at sort of an introduction to this idea that there are three representations of a system. So we had these two vectors. Here we had 3, 1, and 3, 1 corresponded to the movement of a hoverboard. And then we had a magic carpet, which could travel along the vector 1, 2. So this is our magic carpet. And so we were trying to reason ultimately through this idea that it's possible to make it anywhere in this two-dimensional space. And one way of preliminarily assessing that is I can move anywhere along the line corresponding to 1, 2, meaning that for as long as for every mile that I travel east, I travel 2 miles north, I can travel anywhere along this continuum, anywhere along this line. I can move in the opposite direction by just working backwards. But anywhere along that the line that vector is on, I can travel along. Now, same thing goes here. If we extend this hoverboard, we can take that hoverboard in that direction as far as we want. There's nothing that prevents us from, say, just taking a short distance up this vector and then using the hoverboard to start to work my way out further east. And as you do that, we're going to find that what we've essentially created here is a brand new grid system where we can travel anywhere along any line that's parallel to that original blue equation. And the way we can do that is all we have to change is how far along the red we travel. So if, for example, I want to make it to be able to travel along this continuum, then I can take the vector backwards, stop here, and then use my vector to push forward that way. So we've kind of created this slanted grid system now, and you can sort of imagine it with the red as well, because I could take the blue vector, say, back a little distance in this direction, and then use my magic carpet to travel along the 1, 1, 2 vector. So it's as if we've created this, like I said, this brand new grid system. So you can kind of think about each of these little, what would we call these, parallelograms, I suppose. These little parallelograms right here, those are kind of like the new squares within a two-dimensional grid. Now, the way we ultimately set this up, or one way of setting this up, is to say, all right, let's let x, or whatever variable we want, let's say m will denote the number of hours to ride the magic carpet. And we'll let h denote the number of hours to ride the hoverboard. So what we have here is that if for every hour we travel 1 mile east and 2 miles north on the magic carpet, and we ride it for m hours, that means we're going to create m multiples of 1, 2. So for instance, if m was 2 hours, that would mean that I would travel 2 miles east and 4 miles north because, again, I have to make sure that for every 1 mile I travel east, I travel 2 miles north. And then for the hoverboard, we're going to travel h hours, and for each of those h hours, we are going to travel 3 miles east for every 1 mile north. And we're going to add these two together because this is going to be our total distance covered, or total distance vector. And then we wanted to ask, is it possible to make it to any location? Well, let me just create a location here. Let's just make one up for the sake of argument. Let's say we want to make it out here to this point, which we'll just say this is 5, 5. That's the point 5, 5. We want to make it there. Well, we can do that. We can actually take the red vector just to about maybe here, and then take the blue vector the rest of the way. And so the way we would set this up is as such. This is what we call one representation. This is the vector equation. So it's a vector equation because it's an equation equating a bunch of vectors together. Okay, there's a vector equation. That's one representation of a system. But what this really boils down to is when we scale a vector by a constant, remember m is just a number, then we get 1m and 2m inside of that vector. And similarly here, we get 3h and 1h inside of that vector. equals 5, 5. Okay, well, from what we know so far, we know that can be represented as a system of equations. 1m plus 3h has to equal 5. 1m plus 3h equals 5. And then the second equation says that 2m plus 1h equals 5. And hey, by the way, this is a system of linear equations right here. This is a system of linear equations. So we have one representation here, we have a second representation here. The third one is coming. We're not quite ready for that, but the third one is going to be what we call a matrix equation. And that's going to be the third representation. All of these have different visual orientations. The vector equation is this picture right here. The system of linear equations is just two lines, two linear functions intersecting in space. So that one's going to look more like, we would plot our two lines, and I don't know exactly where these two lines are going to cross, but well, maybe something like that and like that. And then we find an intersection point where this intersection point, maybe this is the m axis and the h axis. So this here is some point m comma h. So they're very different visual approaches. M and h tell you how much you're scaling the vectors by before you add them together in the vector equation representation. In the matrix systems of linear equations representation, it's literally thinking about two lines in space and where they intersect to make sure that both equations are true. The third is called a matrix equation, and pretty soon we'll write a times x equals b. We'll actually end up converting this system right here into something that looks like that. But more on that in the coming few videos within this lesson. So we'll see you there.